Hello and welcome to lectures on state space approach to control system analysis and design. So far we studied the mathematical modeling, thereafter representing the systems in standard state space form, solving the state equations, controllability and observability, stability. Thereafter we learned the design of state feedback control for the systems whereby the complete pole placement is guaranteed. We learnt about observers, Neuenberger observer basically, and then we took a different course, a different topic, the multi-rate sampling, and in that we studied three types of controllers: multi-rate output controller, fast output sampling based controller, and periodic output feedback based controller. Now we are coming to state estimation, where we left with Neuenberger observer. In the conclusion, and I have been telling otherwise also, that noise often corrupts the signals. It is a reality, it is found in the signals, in the output. It enters the system along with the input, actuators, etc. In the Neuenberger observer and before that in mathematical modeling, etc., we have not at all given any consideration to noise. Now the Kalman filter, which we are going to study, will be basically considering the noise in the system. And this today's topic is continuous time Kalman filter. In the subsequent topic, subsequent lecture, it will be discrete time Kalman filter. Now, before I actually start my lecture on this continuous time Kalman filter, I will put a kind of disclaimer. Disclaimer number one is that this the Kalman filter requires a deep understanding of statistics, especially the probability theory. The knowledge imparted to us in our education on control systems doesn't cover that probability theory or probability statistics, and so generally our foundation to learn and to practice Kalman filter is little weak. The same is true for me also, that even though I started applying Kalman filter sometime in 1994-95, around that time, in order to make a system for use in nuclear reactors. However, even in the 3 decades of time after that, around 3 decades of time, I have not fully understood the Kalman filter. Because it requires a very deep understanding of statistics, and so far I have not spent time to understand statistics. That is why many of the things in the Kalman filter which we are going to see, we have to sometimes take the things for granted, or we have to subsequently supplement. We have to do some kind of self-study to understand many of the steps of derivation. So with that prelude, let me proceed with the Kalman filter. I show first the references. This whatever I am going to present today in this lecture, whatever I am going to discuss, and in the next lecture, this comes essentially from these 3 references. One is this, the book by Friedland. I have been following quite very much from this book. Many chapters have come from this. I am very fond of this book, very nicely written book. And then remaining these 2. And continuous time Kalman filter derivations, and one example I have taken from this book by T.G. Schultz and J.L. Melsa. It's also a very nice book in control systems, which I find very entertaining to read. Very nicely explained things. Let us proceed ahead. So, as I said in the beginning, we studied the continuous time systems so far without any consideration to noise. No consideration was given to noise. The inputs which are coming to system and the outputs which are coming out of the system, both of these were assumed to be noise free. No consideration was given, and even though the matrices A, B, C state space model utilize this form, nowhere we see any noise. And with that, these were the equations we used. So everything is quite deterministic in the nature. This system state, system input and system output, they have been studied in a pure noise-free environment. We designed controllers, and then we somewhere in the design of a state feedback controller, we realized that to implement a state feedback controller, we require states, and not all the states are accessible or they are not measured for the reasons of economy, installation, etc. So a respite came that Leuenberger observer is capable of estimating the states, and the objective function in that, it estimates the states with this objective that when time t tends to infinity, the deviation of estimated state from the actual state, or this error, will be small. With this objective, Leuenberger observer, we learned. And we went on. We studied the separation principle, which established that when we use the estimated states from Leuenberger observer in place of the actual system states, we get the stability and performance as we would have got with actual states, except for some initial time during which the states of the observer converges actually to the system states. After that, the performance of the system is as good as the performance that would result with the feedback of actual states of the system. Then we also established that the two things, the design of the control and the design of observer, they could be carried out independent of each other, and the overall system with state feedback controller designed separately and observer designed separately, and when they were brought together in realization, the overall system will be stable. This is what we established. We utilize that even for Kalman filter. Now we are at the point where we actually consider the noise associated with measurements. And here in the estimator design, of course, not in modeling, etc. We are not going back. Only in the estimator design. So basically, the design of a state estimator, which we will be learning now, depends upon probabilistic data concerning the noise. Probabilistic data will consist of the average and the covariance, etc. And we will design an optimal estimator which will generate the estimate of states which is best possible with the given noise statistics. That is the beauty. And this is the meaning of the best estimate. This is the meaning that the output of the estimator will be closest to the ideal value despite the presence of the noise, despite the noise corrupting the system characteristics. When we are going to consider the state estimation using Kalman filter, the so-called optimal observer, this is the form of system description. Everything is identical to system description we have seen earlier, except these two things. In noise term, Vt enters at the input terminals. Of course, along with the input, it enters, and it gets integrated, and thereafter, in some manner, it will reflect in the states. Also, another noise, Wt, that corrupts that output of the system as modeled by this part, and that will reflect in the output of the system. The governing equations, they were supposed to be this much. However, in that we have added this, the noise which is entering along with this VUT. So it is the input noise. And the output, this is the how it is getting corrupted because of WT coming there. So both this VT and WT, they are adding to the ideal system which was considered in the absence of the noise. So this is the difference from the treatment or from the discussion we did earlier. In noise VT enters the input. In noise WT, it enters along with the. This VT and WT represent the noise terms which I already told. And of course, one advantage of studying Kalman filtering is that we can study with the same set of equations the theory which is applicable to time invariant as well as time varying systems. So this A, B, the system matrix, the input matrix and the output matrix characterizing the given plant or the system, they need to be linear, but they need not be time invariant, they can be time varying. The derivations we are going to see, they are applicable to time varying systems also. Now, first we see whether you call it properties or you call it assumptions. So the noise which we can handle through Kalman filtering should have these properties. First thing is that it should be additive. As I told earlier, both add one to the input and one to the output. So both are additive in nature, and there are only two forms of noise considered, the VT and the WT, the input noise and the output noise. And the additional properties they should have is both of them are white noise. Now, of course, one should study literature to understand what is white noise, but this is a short explanation. The value of the noise at one time instant is not at all related to the value of noise at some other time instant. In that sense, it is called white. It generally contains, if we see over a long time, it will contain almost all frequency components. The other assumption about both the noise terms VT and WT is that both of them are Gaussian and zero mean. Now what it means that, especially because of Gaussian, all probabilistic information is summed up only in the covariance of the noise. We need not go for higher moments. The moment or the covariance, the second order moment, the covariance is good enough to characterize the noise. So VT and WT, with this assumption that they are Gaussian and zero mean. Zero mean means average will be zero, average taken over some time, and Gaussian means that the characteristic of the noise is fully represented by its covariance. This is the meaning of this. And mathematically it is like this, that expectation of this Vt into Vt transpose is a Q matrix. This V is a vector, mind it, because it is entering at input terminals. It has the same dimensional as the V times U. It has the same dimension. And the U is, let us say, M inputs are there. So this B is multiplying to U, and to that Vt is adding. So it has the same dimension as that of the Bu. And Bu is a column vector. So Vt is also a column vector of the same dimension as the Bu, and which is of the same dimension as Ax, which is of the same dimension as x dot or n. So this Vt has dimension n. And so Vt transpose will be a matrix, and its expectation that covariance is a matrix Q, and we assume that it is positive semi-definite. The output noise Wt again, it has the same size as Cx. It is again a vector of dimension p if the output is p dimensional. So it is a matrix R, and about this our assumption is, we'll see that subsequently in derivations it will be visible that R inverse is to be evaluated, and so R must be positive definite. So these are the mathematical characterization of these properties of Vt and Wt. So covariance is Q. They are uncorrelated from time to time, so that is why this delta. They are zero mean, so that is this. Now they are uncorrelated to each other, so this will be zero for all time, t and tau, for any time. And the initial state of the system is assumed to be having a mean m and covariance p0. So let us interpret this a bit. So xt0, now let us first consider a single state variable. So a single state variable with time, it will have some, let us say, this kind of variation. And then we are considering at t0. So at t0, when we do in the deterministic sense, there is no noise, nothing, then we know that state is here. This is the xt0. We are considering one of the states, so let us say xi. Now when we say that it is containing noise and its expectation is m, so of course this is m, but then what it means that it could be little more or it could be little less, and that this band is something which is very random. However, the mean is here, and then that around that its covariance, which is covariance is p0. So this one has, fading, means at this it has highest probability. Let me draw a little bit. Here it has the highest probability of being found. As we go away from this, its probability goes on reducing, and that is what is reflected in p0. Now in a two-dimensional, let us say this is two-dimensional, at some time t0, we expected the state to be here, let us say. at this point. So this is when we know deterministic, the state is here, that is how we'll say. But now we are saying we expect it to be there. And so it can be found anywhere around this. And this region around which it is there, that in where it is there, that is characterized by this P0. So essentially we need to tell in much more better way if we are, our foundation in statistics is better, but this is a crude understanding that the state is found in a two-dimensional space in a kind of circle with high probability of being found here, and as it goes away the probability goes on reducing. In a three-dimensional space it will be a sphere, and in a multi-dimensional space a hypersphere. So this is the meaning of this and this. And at xt0, this initial condition xt0 is assumed to be independent of the noise terms Vt and Wt. So that means if we look at this kind of expectations, they will be 0. This is again the assumption or properties, whatever we take it as. Now with that we estimate the estimation, we state the estimation problem, optimal estimation problem. So we are given ut and yt from t0 to t1 at all the instants of time between t0 and t1. Ut and yt are continuously given, and we are also given with the probabilistic description of xt0, vt and wt, means mean and that covariance, that q and r and p matrices, p, q and r matrices, this is given, and the mean are assumed to be 0, or if they are non-zero they are given. So we have the knowledge of input and output at this time interval, and we have the statistical information, probabilistic description of the initial state, the input noise and the output noise. And now we first consider the case of autonomous system. So we are assuming u equal to 0 all the time during this interval. We assume ut to be 0, and we are also assuming that instead of estimating the entire state, entire set of state variables x1, x2, etc., we are considering a linear combination of states, a weighted sum of states. So just one quantity we are considering to estimate, which is vxt. V is a vector. We are not first considering the entire state vector xt. We are considering a weighted sum. So we want to estimate in this situation, means now as I said we have assumed the system to be autonomous, ut to be 0 all the time during this interval. So we are given the information about output, we are given the probabilistic description of the initial state, the input and the output, and we want to estimate a linear combination of states bxt. That is the problem, and it has to be obtained in such a way that this objective function, this integral, this index, performance index, is minimized. It has to be done. And you can see we are assuming that this beta, which is the estimate of bx1 in the optimal sense, is given like this. Now this requires a deep understanding of statistics. We are taking it as a granted that we want to estimate beta, which is a function psi of t given b and given t1, and this beta will be this integral, a function of psi multiplying with y integrated with respect to time over the interval t0 to t1, we will get a beta which is the best estimate, minimum variance estimate of this linear combination. So this is the starting point, and as I said, this we are taking for granted that it will come in this form. And as we will see, with this we get the solution, we get the result. So it is a good starting point. In other words, we have to minimize the square of this deviation of bx1 from this integral. This expectation has to be minimized. And it has to be done for any arbitrary b and any t1. So that it means it should be applicable for all types of linear combinations of states, and at all the time from t0 to t1, it should be any t1, it should be applicable. T1 can be small, T1 can be large, but it only to be finite and it should be applicable. So again, something we assume, and we consider that a state RT which has the same dimension as of xt, we have this equation. We assume a new state RT of dimension xt which is being governed by this equation, and what we see is that this A is the matrix which is governing also the dynamics of state x, and C is that output matrix. So this R will have something to do with x. That is something we should register, and we take this dynamic system in which the state variable is R and its boundary condition is given. Generally in the state equation we give the initial condition. Here we are giving the value at t1, the final time, as B transpose. This is the assumption, and B was that, if you go back, B was here, that linear combination Bxt. So we are telling that RT is some kind of state. It has same dimension as x. It is governed by this. The forcing function is C transpose psi transpose. The system matrix is minus A transpose, and the boundary condition is RT1 is B transpose. This I have already said. Now we consider this product R transpose into X, and we are differentiating it. Why we are doing it, it will be little clear, but essentially we want to get a linear that integral, that minimum variance, that bxt minus that integral. We want to get one expression for that. With that objective in mind, we are proceeding like this. We assume this system dynamics, and this state we are multiplying its transpose to state x, and that product we are differentiating with respect to time. So this is very simple. Differentiation of RT xt is R dot x and R transpose x dot. And in that, in place of R dot, we make a substitution from here, this one, and x dot, we have assumed autonomous system, so Ax plus Vt only remains. That But is not coming because we have assumed ut equal to 0. So we have made these substitutions. We get the products. So this R transpose T80 and R transpose T8 xt, this xt, R transpose T80 xt, R transpose T80 xt, they will cancel. and what remains is psi t ct xt, which is here, and this r transpose t vt, which is here. These two terms remain, and ct xt we realize is yt minus wt, because that y is cx plus w. So cx is y minus w, we do that substitution, and rt vt as it is. And now we open this, so we get psi t yt minus psi t wt plus r transpose v. This is what we get rewritten here. Now we proceed further. We integrate both the sides, all the terms on both the sides between these lower and upper limits t0 to t1, and we have the boundary condition rt1 equal to b transpose. So this is here, this is the integration of this left hand side is integration of d dt of r transpose x, and this becomes this evaluated at t1, that comes from calculus. So integration of derivative is the one evaluated, the expression integrand evaluated at upper limit of the integral, so we have this, and then this evaluated at lower limit of the integral, and this rt into xt and rt0 xt0 r transpose, so this becomes equal to bxt1, and this is as it is. So we get that, and the RHS is integral of this, integral of this, integral of this, which is written here, and of course we will consider them both have to be equated. So this is the integral of the LHS, this is the integral of the RHS, they are equated to each other. And now what we do is we take this term psi and y wala term, this term to the left, and this one we take to the right, and we rearrange. This we have seen before. Our intention was to get something about that only. So we have taken this to left, and we have this difference, and remaining these three terms are here. Now we square them and we take the expectation. Now again here there is something we have to accept, and we have to get the explanation by referring to advanced mathematics, statistics, etc. So what we do is we have squared the left hand side and we want to take its expectation, that is fine. But what we have done is this whole thing is square, its expectation we are telling will be equal to expectation of the individual terms squared. This is something we have to supplement by reading further. But here we take it that expectation of left hand side square, that is fine, equal to expectation of this square, which is equal to sum of expectations of individual terms squared. With that we proceed, and we will now evaluate each of them separately. So first one is R transpose xt0. R transpose xt0, expectation of its square. So this is R transpose xt0 into transpose of R transpose xt0, which is x transpose R transpose. And because R is something deterministic, so it is R transpose and R taken out, and expectation of xt0 x transpose t0, and this we have seen it is p0. So we make that substitution. So one of the terms becomes this, The second term we proceed is this, and again from mathematics, that expectation of square of this integral is double integral expectation of that. So expectation of some integral squared is equal to expectation of double integral of this integrand and the transpose of the integrand. So a double integral, and in that what we see that because again this psi and w are independent, so we take psi out on both the sides, and remaining term is expectation of w transpose, which is r, and of course r is there, and this double integral will get changed to a single integral because this will be delta t minus tau will exist only at t equal to tau. So we will get this one. This expectation becomes integral of psi r psi transpose with respect to dt. We get that. The third one is done in a similar manner to first one. RT Vt r transpose into v, integral of that its square, and expectation of that will be integral of RT into q into r transpose q r, very similar to what happened here in the first term. So we have now three integrals ready, and LHS was also integrated. So we rewrite all the things together. So this was the expression from where we started, and each one of them we evaluated separately. So we get this one, that this left hand side, this becomes equal to this term plus this term plus this term, and these two both are integrated with respect to dt, and both have the same limits of integral, so they can be combined together to get this, and this term is as it is. This has a lot of resemblance with something which has seen earlier, that will be shown in the next slide, but let us recapitulate a recap of what we have done so far. We have seen so many complex mathematical equations, something sound to see and something not easy and taken for granted. So we have the system description with additive noise. We had the knowledge covariance q, r and t0. We assumed a state equation like this and a boundary condition like this. We posed the estimation problem as the problem for estimating a linear combination of the states at time t1, and then we intend finally to say that for any b and for any t1 it should work, and it should work from any t0 to any t1. So now with that recapitulation, we come back to restate the problem like this, that now we have to minimize this, which is derived to be like this, and the psi is coming here, C transpose psi, it is exciting this system, this we had assumed. So now this whole thing seen together appears like a regulator problem which we had seen a few weeks earlier, with two differences. One difference is that generally this is given in the regulator problem at terminal time. Here it is given at initial time. And other difference is that RT, generally state equation is given with an initial condition. Here it is given as a terminal time, final time t1, a boundary condition is given. So otherwise it is like a regulator problem. So now we leave a lot of gaps and we straight away say that it's on similar lines as in case of regulator problem, it will have a solution similar to that. So psi transpose will be expressed like this: R inverse C into P. In the regulator problem, it was R inverse B transpose P. Here, because it is the output matrix we are considering, it is R inverse CP. And this P comes from solution of this Riccati equation with this initial condition, and we want positive definite solution. So so the solution to this problem, I go back to previous slide. The solution to the problem of optimal estimation to minimize this performance objective for this system is this, where this P is solution of this positive definite solution of this Riccati equation with this initial condition PD0 equal to 0. Once we have the solution of this Riccati equation, we know P, then we can substitute psi in that equation for R, and so we have R given by this dynamic equation with this boundary condition rather than the initial condition. We get R given by this, and we can rewrite it by introducing a matrix AE as A minus this. This is that psi transpose rather. So we introduce AE, and its state transition matrix we denote by phi E. Then RT will be given by this. This B is the final condition. RT1 was B. So RT is given by this state transition matrix, pre-multiplying that final condition, and psi is given by this. We have substituted R. Here it was psi. One more. Psi was this, and we substitute R there. So we get this. This is R and this is psi. So we get this for psi, and once psi is known, then we know beta, which can be determined. So thus we have arrived some meaningful result, and from that now we want to see that how we can estimate all the components of the state vector. So far we concentrated upon a Bx at t equal to t1. Now we see how we can estimate all the components of x at t1 or probably at every time t. So we assume that B is EI. EI is the elementary row vector. So it has all zeros. Somewhere it has 1. So at the ith location it is 1. Remaining all locations it is 0. This is EI. So in that case Bxt1 will be Xit1, because we have, let us say, 3-dimensional 001 into x1, x2, x3 will give x3. So similarly in a, let us say, 0, 1, 0, 0, 4-dimensional x1, x2, x3, x4, this thing gives x2. So Bxt1 with B as EI is Xi, ith state. And that means that Xit1 will become this. And substituting for psi, we get this. And now if we do for different EIs, EI equal E1, E2, etc., we take them together, then we will get entire X. And that entire X, the estimate of X, we are denoting by XE. XE is estimate of X. Will be given by this. We got this result. Now we have to do so that it becomes recursive, it becomes realizable. So what we do is we differentiate this expression, both the sides, and we get this result with that definition of K, which is given here. This one we are denoting by K. And if we differentiate this, again we have to know a few properties of integral calculus, that how by differentiating this, of course we will get XC dot differentiation of this, but how from this we get this, where AE and phi E, that phi E is STM corresponding to AE, that we have seen. So from this by differentiation we will come to this. And of course that Kalman gain KE is given by this expression, and AE is closed loop system matrix with KE and C. So we got basically a closed loop equation given by this one, and the Kalman gain given by this one, where P is obtained by, it was there in the previous slides, solving a matrix Riccati equation, initial condition was known, and that means that we can estimate XE by this. Let us see its resemblance. It is very similar to the observer equation in case of a Duenberger observer. Estimated state is governed by AX plus this. This is a prediction. Of course, we did not yet consider that BU term. So if we know XC at some time t, we can find out at subsequent times. And the differential equation is x dot equal to AX. We have assumed 0. So x dot equal to AX will give prediction of the state. However, that is only a prediction. It can be corrected with this. This is the difference of the model output. C into XE is something similar to Y, the output, but it is output of the system with the mathematical equations. And this is the output of the actual system of the plant. So this is the deviation of output from the actual output, that multiplying with KE will apply correction, and we will get a good estimate, the best estimate, which will minimize that variance which we saw in the previous slides. That is the all about Kalman filtering, which I have understood for continuous time linear systems. We restate in the form of a summary that we are given this equation with this noise and this output equation with this noise. Covariances Q, R and the initial state are assumed to be known, and this PT0 is this one. Now we solve this Riccati equation for PT, which is expected. We will accept only the positive definite solution PT from this, and then we will determine KE once P is known, C and R are already known. So we will determine the Kalman gain KE, and then the state of the estimator is given, estimated state is given here. XE equal to AXE plus KE into CX minus Y. So This is the summary of optimal estimation in case of unforced system. We had assumed if we do a similar derivations with ut not equal to 0, that means the forced system, almost everything remains the same. Only two equations change. One is this equation, the state equations characterizing the system. So we get this term back. This is given as it is. This Riccati equation is as it is, which was there in case of unforced system. This Kalman gain computation is as it is, which was there in the unforced system. Only in case of estimated state, we get back again this B into E. Rest all the derivations will remain identical. And once we have done the forced system, we have done the unforced system, then we are ready to write the forced system only by these two small differences. Rest all the things are identical. This matrix Riccati equation is identical. This solution of gain is identical. This is all about Kalman filter equations. So once again, this is the given system, this is the noise, this is the output equation, this is the noise. We know Q and R characterizing the two noise terms, that covariances. We know xt0 with some uncertainty or some error, so we have pt0. We solve this Riccati equation given this initial condition. We accept the positive definite solution. Plug that positive definite solution in this, get Ke, and with the measurement, availability of measurement, this difference pre-multiplied with the Kalman gain Ke and added to this ideal response of the system, we get the corrected response. So this is the predicted response, and this is the correction to this, and so we get the estimate. And because K is calculated so as to minimize that variance, this is the optimal estimate XE. Now let us proceed to see how it is realized, how it is implemented. So this is the system. X dot equal to AX plus BU, and in that noise was coming. So this system, we are getting the output. So this is the physical system, and of course that is characterized by matrices A, D and C. They may be time varying. So we have the knowledge of those matrices A, B and C. We solve the response of the system with respect to X dot equal to AX plus BU using this state equation. Now, having solved this X or having predicted X, we calculate CX, which is here. We compare it with Y and get the error. That error we multiply with Ke and we get the correction. So this plus correction, and this is how it can work continuously online, and it can go on giving the estimate XE. So XE is the estimate of this X, and it can be used for various purposes. For the purpose of estimating for the purpose of implementing a state feedback, for the purpose of fault analysis, etc. It has various applications. We see what happens in case of a linear time invariant system. So as we know that in case of a linear time invariant system, the matrices A, B, C characterizing the system, they are constant matrices. Q and R are assumed to be constant too, and T0 is minus infinity, a time in the infinite past. So in that case, with all these things constant, A, B, C constant and T0 and infinite time in the past, that matrix Riccati equation reduces to algebraic Riccati equation, this one, which has a unique solution for P. So we get the P and we have that K relating to P. So Kalman gain can be calculated, which is also constant. So K will also be constant. So it has to be, this calculation has to be done only once, and the Kalman filter can be implemented just with fixed K, and it will do the estimation even in the presence of noise. Now we consider one example, a second order system given by this state equation. A matrix is this, B matrix is this, and we are measuring the second state. This is C matrix. And we have the knowledge of the noise Vt and Wt. So Vt is the additive white noise at the input, so it has the covariance Q. And Wt is a white noise with covariance R adding at the output. So Q and R are covariances characterizing the noise terms at the input and output respectively. And with this one, we see that E of Vt, V transpose will be this 2 by 2 matrix. And of course, this is that Q matrix in our derivations, and we see that this is positive semi-definite. And R we are assuming not equal to 0 here, this R not equal to 0. So it is positive definite and positive of course. So when we do that, AP plus PA transpose minus, let me go back, I also do not remember, but I have it written on this piece of paper. AP plus PA transpose minus PC transpose R inverse CP plus Q is the steady state form of the Riccati equation or algebraic Riccati equation. In that we substitute A here, P which is this. Of course, this is supposed to be a symmetric, so this P21 will be P12. This also it will be P12. P is a symmetric matrix. So this is AP, this is PA transpose, and this is R inverse is 1 by R, and this is P, this is C transpose, this is C, this is P, and this is Q. So we evaluate this, we will get three equations, this one, this one, this one. The positive definite solution is to be accepted. So we first solve this, which will give a positive solution and a negative solution. However, that negative solution will not be acceptable because that negative solution will give a, if we do that and if we obtain that full P matrix with that negative solution, P will not come positive definite. So we will accept the solution of this equation which gives P12 positive. So, and that one we will substitute, we will evaluate the solution from the second equation. P12 obtained, we can get P22 from here, and then P12, P22 known, we will know P11 from here. So we get these solutions. And now we get the gain K, which is that R inverse CP transpose. This is K, the Kalman gain K, and it becomes this. We can evaluate this for, let us say, Q equal to 16 and R equal to 1, and then Kalman gain K becomes this. And with that, the closed loop system matrix in that A and KC transpose, C transpose K will become this, and we can check it is stable. And because this was a linear time invariant system, we required, and with noise statistics Q and R constant, so because of all this, we required estimating Ke only once, and that will be applicable throughout for any T. So this K has been estimated optimally. That is the difference from the Leonberger observer. In that, the K was designed so as to stabilize the observer. Here this K is designed to minimize that error, state estimation error squared. And it will lead to a stable system also. That is proved in literature. So with that, we come to the end of this lecture. There is no specific summary given here. Only thing I want to tell here is that despite the derivations being very complicated, despite many things not understood, what remains the reality is that Kalman filter is something which applies in so many areas. It has tremendous applications, numerous applications, and it gives the estimate of state in noisy situations, and sometimes even with some uncertainty in matrices A, B and C. It generates the best possible estimate. That is the reason it has so much popularity, so much utility, and so many applications in various scenarios, in nuclear industry, in chemical industry, in aviation, in defense applications. Everywhere one will find a Kalman filter. Thank you very much. We will again meet in our next lecture, which will be on discrete time Kalman filter. Thank you.